Hello, welcome. This is Dr. Schleif with another worked example, and we're looking at some uncertainty calculations today. This question reads, the volume V of the wire is given by the expression V equals pi d squared L over 4. The diameter, length, and mass M are measured to determine the density of the metal of the wire. The measured values are, and there's a list of both the value D, L, and M. Calculate the density of the metal with its absolute uncertainty. Give your answer to an appropriate number of significant figures. Got a writing tool here. So epic pen. Maybe one of these days it'll become a legendary pen, a mythical pen. Still waiting for that. All right. So we start out with sort of the definition of density. We use the Greek letter rho for density, and we know that it is mass. They're calling it capital M over the volume. And the volume is given by this expression right here. All right, so let's just sort of calculate the mass per volume, but in the units that are sort of, we're restricted to down here, kilograms per cubic meter. So a quick conversion of the mass here from grams to kilograms, we can say that if we have something that's 0.225 grams, very formally, we could write up a conversion like this, that there are 1,000 grams per kilogram. So we're dividing this by 1,000, effectively moving the decimal point over 3 places, right? So we're gonna go 1, 2, 3, 1, 2, 3 zeros. And so the mass is 0.000225 kilograms. And so far, so good with the numerator. The volume, we'll sort of use this expression to calculate. And so we've got pi times, and now the diameter D here is given in millimeters and the length is given in centimeters. And those are sensible because the diameter of a wire is going to be pretty small compared to the length. And so those are sensible units if we're measuring. But to get it into cubic meters, we're going to want to sort of make these conversions. We had talked previously about converting one or the other. Converting centimeters into millimeters or millimeters into centimeters, and then calculating the volume in those units and then converting it into cubic meters. But you could also just convert each of these into meters and then sort of plug it in here. So we'll take a look at that and field any questions about any other methods you might have a question on. Just leave it down in the comments below. And while you're at it, don't forget to hit that like button, subscribe, get on the Dr. Schleif notification squad. Don't miss out on all the worked examples for your ACE physics needs. All right, so we're going to substitute in for D here, 0.38, and we can convert this lowercase m, milli, just 10 to the negative 3, right? So D is 0.38 millimeters squared, right? So this quantity D is squared, and then times L is 25 centimeters, and so 25 centi is 10 to the negative 2. So here we're saying the Greek, I'm sorry, not the Greek prefix, but the metric prefix centi, C, just means 10 to the negative 2. Milli, M, is 10 to the negative 3. If you haven't already committed the metric prefixes in their corresponding order of 10 to memory, now's a good time to do that. So we've got, micro, 10 to the negative 6, nano, 10 to the negative 9, mega, 10 to the positive 6, kilo, 10 to the positive 3, giga, 10 to the positive 9. We'll go over this. In fact, you can click the link above if you want to see this explained in a different video. And so this is in meters here too, right? So you have 25 centimeters, that's L, and then all of this is going to be over 4. I will calculate this with an on-screen calculator so that you can kind of see that in front of you if you're following along at home. Let's clean this up just a little bit here now that we've discussed that. So we've got let's actually do this over here. All right, so I'm calculating this right here. We got 0.38 times 10 raised to the negative 3, right? And so that's this number right here, right? 0.00038. But I want to square that, so I'll find my x squared e, right? Now I'm going to multiply it by Now 25 times 10 to the negative 2, I can kind of, I could either use grouping symbols and type it in just the way that it looks, but I can pretty well just say, well, that's times 0.25. In other words, 25 centimeters is 0.25 meters. And if you were to, plug that in, that's what it would become. So far, I've just taken the product of these terms here. Still got a pi up there, so times it by pi. So there's my numerator, 1.13. And now I got to divide it by 4. So we now get a volume of, tough to see there, but 2.84 by 10 to the negative 8. And because these meters are squared and there's meters here, we can see that the units that fall out of this are cubic meters, right? And so we have kilograms per cubic meter, and that's a very convenient way to think about doing those conversions from centimeters and millimeters into meters to give yourself the correct units of volume. All right, and so we've got our calculation down here for density, the mass divided by the volume in the preferred units. That calculator. All right, so we've got 0.000225 divided by, open parentheses here, 2.84 by 10 raised to the negative 8. Dividing by quantities in scientific notation, it's very important that you use grouping symbols, because otherwise your calculator will divide by this quantity first and then it will multiply by 10 to the negative 8, whereas you're trying to divide by the entire thing there, right? So you use grouping symbols. You get final density here of, looks like 7,922. .535. So this would be like a calculator value. Now we're going to decide to what level of significance we can report this to, and we're going to sort of use the uncertainties in order to judge that. Now we want to sort of think about the reasonableness of this. That seems like a pretty high density, 7,922 kilograms per cubic meter. But kilograms per cubic meter, right? So maybe that's not too far outside the realm of possibility, all right? Because it is a metal. All right, so let's go ahead and consider the uncertainties now. There is uncertainty in our final answer. There's contributions to the uncertainty from both the mass and from the length and from the diameter. All of these measurements contribute to the final uncertainty in our final answer. And so let's see how we deal with them. The first thing that you want to do is determine the percent uncertainty in each one of these readings, right? So we're given the measured value and the absolute uncertainty. And you may recall that the percent uncertainty is calculated as the absolute uncertainty, which is this, divided by the measured value, okay, which is this. So for D, we're going to set it up like 0.01 over 0.38 times 100%, and that'll give us the percent uncertainty in D. Cleaning this up a little bit here. Actually, let's go ahead and just set them all up while we're thinking about it. So L is going to be what? 0.1 over 25 times 100%. And M down here is going to be 0.001 over 0.225 times 100%, right? And so this will give us the percent uncertainty in each one of the measured values. Let's calculate them all together here. All right. Going to a little bit better spot there, maybe. All right, so the first one we've got 0.01 divided by 0.38 equals times 100. So this one is 2.63%. Okay, so we have a percent uncertainty contribution from the diameter measurement, 2.63%. So that one's 2.63%. The next one was the length L. So that's going to be 0.1 divided by 25 times 100. Add a percent sign, 0.4%. So there's only 0.4%, less than half a percent uncertainty from L. 2.63%. Okay, was the first one. Lastly, we have 0.001 divided by 0.225. Times 100, add a percent sign, 0.44 repeating percent. All right, so we've got all of our percent uncertainties calculated. Now we have to think about combining uncertainties, okay? We always are going to add percent uncertainties when we're multiplying or dividing values in our calculations. And that's exactly what we're doing here. So if you think about like what we did to calculate, for example, just the volume. The volume, we had to multiply, so, you know, the diameter times itself times L. And for the mass, and then we had to, you know, sort of divide that volume into the mass, right? So there's lots of operations that occurred there, and we have to account for it as many times. So for example, if there's 2.63% uncertainty from the diameter, but the diameter is squared, we have to recognize that the total percent uncertainty in our final answer, which remember is this, the calculator value, there's actually twice this uncertainty from this measurement, and that's because it's squared. Likewise, if there was a quantity that was cubed, we have to triple the percent uncertainty. In other words, you have to account for that percent uncertainty each time it shows up in the equation. If we were to expand this sort of clumsily, you know, we could like so say, okay, there's 2.63 from this measurement of D, there's another 2.63 from that measurement of D, there's 0.4% from that measurement of L, and there's 0.44% from this mass, right? Because remember, we're solving for the absolute uncertainty in the density. So the mass contributes to that, and everything that went into the volume calculation also contributes, all right? So if you're following along at home, why don't you add up the percent uncertainties right along with me, and we'll compare notes. All right, so I've got my 2.63%, but I'm going to double it, right, because D is squared. And I'm going to add in my 0.4 for my L measurement. I'm going to add in 0.44. I'll expand on that. I'm going to get 6.1% uncertainty. So we talked about the other day, you know, how do you report your data? Well, you can either report it, you know, measured value plus or minus absolute, but we have here what we calculated plus or minus the percent uncertainty. Now I'm going to call that 6.1%. Okay. But we want the absolute uncertainty. If we look at sort of the way that our answer line here is given, we want the value plus or minus the absolute uncertainty. I think it tells you to, you know, with its absolute uncertainty in the question. All right, so we're going to take this percent of that number. All right, so if we make 6.1 a percentage, then it's going to be our 7,922.535, but let's take 6.1% of it. Oh, let's type it in correctly. 7,922.535 times 0.061, right? So we're taking 6.1% of 7,922 to get 483. All right, let me rewrite this up here. 7,922 plus or minus 483. So basically, we're certain in the hundreds place. In other words, our uncertainty is here in the hundreds place. And so we have to round this thing off at the hundreds place. All right, and so we're going to change this answer now to 7,900, right? Because rounding this to the nearest hundred, it would be 7,900. And then rounding this to the hundreds place, we'd say it's plus or minus 500. All right, so we're really saying that the density could be as low as what, 7,400, Or if we added 500 to this, it could be as high as 8,400. All right, so final answer now, 7,900 plus or minus 500. Anytime you're doing a practice calculation, you always want to give yourself some feedback on this. And so what I'm going to do now is go ahead and change this question paper over to the mark scheme. So this is question 1 from paper 21 that was administered in May, June of 2016. So let's go ahead and queue up the mark scheme and see if we see 7,900 plus or minus 500. If we do, we know we did it right, and that's good, and we can study that. And if we got anything, if there's anything else in the mark scheme, then we have to go back and check our work and see maybe where we made a mistake. So let's take a look at what the mark scheme shows. So they give an answer here, 7.9 plus or minus 0.5, and then they put the times 10 to the 3 kilograms per cubic meter sort of out here. It says, or exactly the way we wrote it, right? 7,900 plus or minus 500. Okay. And so that's the way that we go about combining percent uncertainties and treating calculated values with the uncertainties that went into the calculation. This has been another worked example with Dr. Schleif. Still living the physics life, and we'll see you next time.